So on 1.7's bookwork assignment, which is I think page 70, if we look at number 57, I feel like I didn't do a stellar job of explaining this because it was like the very end of our lesson yesterday. And it gives you a drawn representation of a function, and I believe the function is x squared minus 6. Does anybody have that in front of them right now? Okay, great. So it is x squared minus 6. And it gives you a block of information as far as like what the directions are. It says, determine whether this is a one-to-one function. So the test for whether you have a one-to-one function is it has to pass the horizontal and the vertical line test. So we know from our memory that this is a parabola who has been shifted, whoops, down 6. And clearly it passes the vertical line test, but is this going to pass the horizontal line test? No, it is not. So this is not a one-to-one function, which earlier in our notes was good news because that meant I just got to say something like, inverse function does not exist, and then I walked away. Well, if you keep reading in the instructions, it does say if it's not a one-to-one function, restrict the original function's domain so that way you can create an inverse function. So in my answer key, I kind of wrote a note to you like, this is how I restricted it, but you can do other things. What I usually do is I just erase half the parabola in this case. So I just come through and I pretend like none of this existed. And I start the function right here. Because that would surely pass the horizontal and vertical line test. So I'm going to write myself a little note. This is if your x's are greater than or equal to 0, you only have half of a parabola. So let's think about everything I know about functions and their inverses. I know that the x's and y's switch. So if I'm trying to find the inverse function, that means I have to turn the function inside out. X equals y squared minus 6. You're going to add the 6 over. And then your last step would be to square root. Now, I know algebraically when I'm solving, I'm supposed to do something with plus or minus here. But that's not going to be the case in this particular function because remember how we restricted the domain? And we only had x's that were greater than or equal to 0. So you can't have negative values. So therefore, I'm going to leave the negative part of the plus and minus off. So the inverse function is x plus 6. But it does say very clearly in the instructions, you have to give any domain restrictions. So guys, think about this. The domain of this original function, whoops, goes from 0 to infinity, because that's what I chose to cut it off at. The range of this original function goes from negative 6 to infinity. So what does that mean for my inverse? Well, inverses have x's and y's that switch, so that also means the domain and range are going to switch. So your inverse function is going to have a domain that matches the range of the original function. So it's negative 6 to infinity. Now, you could have figured out that domain simply by graphing it. Remember, you can just switch ordered pairs around. You could just graph a square root graph that's been shifted left 6. There's a lot of ways to get to that answer. But you have to kind of bring it down to the basics for inverses. Inverse functions, the most basic property of inverse functions are that the x's and y's switch. So you should be able to figure out everything you need to know based on just x's and y's switching. I will tell you number 58, a little more exciting. It's an absolute value graph. So when you go to find a cutoff absolute value graph, think about this, guys. An absolute value graph are those V-shaped things. So if you were to cut off a whole half of the V, what do you have? A line, essentially. A ray, technically, but a line. So when you go to find the function, you're not going to be able to algebraically find the function. Like switching x and y is not going to work. You're going to have to just visualize it and then come up with the equation, kind of like you did when you had a piecewise function. Okay? So have fun with that. All right, your lesson 2.1. We're going to be working on the graphing calculator a bit today. What I've learned from first hour is that this lesson is lengthy, so when we can save time, I'm going to save you some time. Now, this first example in your notes is already done for you, so we're just going to kind of have some commentary on whether we agree with these answers or not. The title to this section is they're graphing power functions, and then we're also going to be solving radical equations in a minute. these are all examples of power functions. So any variable raised to a power can be considered a power function, but when you look at the type of power it is, that changes the type of function you have. So like for instance here, a positive integer power is just going to create a polynomial. That's boring. But if you have a fraction or a rational exponent, all of a sudden you become a radical equation, which looks very different. And then there's another example of a radical equation that is still technically a power. And we'll talk about what happens when your powers are negative in a minute. So this first example, they wanted you to graph 1/3 x to the third power, which they already did for you. Not a big surprise to see that that's a cubic function who's been vertically compressed by 1/3. They plotted some points for you apparently, and they came up with domain and range from -infinity to +infinity. Yep, we would have said that too, so good for them. Now this is where I don't really like what they did here in your book. They said intercept 0. Well, that's a little vague for me, guys, because what intercept are they referring to? In this case, both, but they should have probably specified like x-intercept and y-intercept. The problem is because it went through the origin, both the x-intercept and the y-intercept are at 0. So that's an acceptable answer. I will warn you, though, that we're going to have some differing of opinion as to who's an intercept coming up here. End behavior, this is from the old textbook, and they use the old notation for end behavior. We're going to come back and use our normal end behavior template that we have been using for about a month now. And then it's going to ask you whether your function is continuous or not. It is continuous. You can sometimes look at the function. That one's clearly continuous. But also we're going to look at the algebra of the function to determine discontinuities. You guys are looking for asymptotes, holes, and jumps. Any of those would be discontinuities for you. All right. Skip around. Let's get to number 1. I'm going to spoil this for you. When you graph this, it looks like this. So give yourself a little sketch. Now that kind of looks like a parabola. I did a really bad job of graphing that. That was really awful. This is not quite a parabola though, right, guys? This is a quartic function to the 4th power. And what's going to happen is the vertex part of this graph is going to kind of hang around the origin for a while and then come back. We'll discuss that in a moment. All right, domain. How far left, how far right? Yeah, -infinity to infinity. Range. So it stops here at 0. So 0, or it starts, I should say. The range starts at 0, goes to infinity. Intercepts. Okay, I would like you to split this into the x-intercept and the y-intercept. Now this is where your textbook is going to differ from other textbooks. I agree with your textbook if you're looking for an opinion. The true definition of an x-intercept is where a function changes from positive output value to negative output value. So it has to go through the x-axis from positive to negative or negative to positive. Does this function do that? It does not. Do you remember what happens here? It like bounces off. We learned a little bit about this in Honors Algebra 2. My regular Algebra 2 kids have never seen this before probably. So in your textbook's definition of x-intercept, there's actually none. However, if you said, you know what, Abruzzo, I'm going to say there's an x-intercept at 0. For today, I'm not going to mark you wrong, but I just want you to make a little mental note. Technically, there's no x-intercept there. The y-intercept, however, though, that does exist. It crosses straight through the y-axis at 0. So if we strictly think about the definition of x-intercept, this one doesn't have one. All right, end behavior. You're going to use your template of f of x approaches something as x goes to the left, and your function approaches something as you read x's to the right. All right, so talk to me about your left behavior. If you look on the left side of your function, where's it going? Up, up, up to infinity, good. And on the right side of your function, it is also going up to infinity. So intercepts and behavior. All right, continuity. Does that look like a smooth continuous curve to you? Yeah, so yes, continuous. And then the last question is an oldie but a goodie. Increasing versus decreasing behavior. So remember from your work, these are domain intervals, and it's like the roller coaster question. So there is a minimum value here, a turning point at 0, 0. And if you kind of got this wrong on the test last time, I probably wrote you a note. Remember, we're only supposed to be using x values because it is a domain interval. If you forgot that, you would kind of luck out though, because both x and y are 0. But remember, the place where it changes its behavior is at x equals 0. So when is your function increasing? When is it a roller coaster going up? I heard 0 to infinity. Good. And it's decreasing from negative infinity and then stops at 0. And remember, on those intervals, I prefer you guys to use parentheses, because at the turning point, your function is neither increasing nor decreasing technically. And just for funsies, it didn't ask this, but I'm gonna. Concave up or concave down? Concave up. That's a big smiley face. Concave up the whole time. All right. So what if I throw, yes?
On standardized tests,
yes.
we also consider roots to be if a point crosses from positive to negative.
That's a good question. So vocab issue is a root and a solution are synonyms in math. X-intercepts and roots are not. So you can be a root or a solution to a function, but you could not be an x-intercept at times. And we're going to discuss this at length when we get to the end of this chapter. Because right now I'm not picky about it, guys, but in a couple of weeks I'm going to be super picky about it. Like when it crosses through from positive to negative, you have an intercept. Yes, very good. Talk about multiplicity in that one. That's a good lesson. I like that lesson. All right, good question. All right, number 2. So I wonder what happens when your exponent is negative. Well, you guys, you already know what happens when your exponent is negative. Doesn't that just take the term and move it to the other side of the fraction bar? So this x to the positive third power will move down to the numerator. So you're really going to be graphing this function. And if you don't remember what that looks like, you can type either one of these functions into y equals, because your calculator does it all, and you get, I already forgot what this looks like. This. You get a rational function. Oops, I did a really bad job of graphing. What's new? Let's talk about domain. Kids, for some reason, are like bamboozled by this one. They're like, oh, it goes everywhere. Okay, if you say negative infinity to infinity, you're telling me like it's a smooth continual curve. Is that a continuous curve? There's like some weird stuff happening right in the middle of it. So the domain, while it does go forever left, it starts at negative infinity. It has a discontinuity at 0. Well, now that I look at the algebra, oh, pen, are you not going to work? Come on, buddy. Now that I look at the algebra, I think to myself, yeah, because what would happen if you used x equals 0 in that denominator? You would get divide by 0, which we know is a discontinuity. So the domain goes from negative infinity to 0, skip over 0, 0 to infinity. How about the range? It doesn't, it's not going to continually go from low to high, right? There's a break right here, a horizontal asymptote. So the range is actually the same as the domain, but this time it's measuring y values. So the range goes forever low, and then at 0, it hops over an asymptote and then continues on. So be careful about your interval notation if there's a break. You got to show me the break in your interval too. Okay, intercepts. Do you see it crossing the y-axis at all? Me neither. Do you see it crossing the x-axis at all? Me neither. So there's none. Sometimes there's none, and that's okay. End behavior. It's our end behavior template. Here we go. Don't you wish you had a stamp for this? I do. You know, I've asked this for years now. One day some kid's going to get me an end behavior stamp. I'm just kidding. I don't have a use for that. I read on a computer. What am I going to do with an end behavior stamp? All right. Maybe back in the day. All right, guys, on the left side, be careful. Your function is approaching a y value. Can you tell what it's approaching? It's scooting up to that asymptote, which is at 0. Now, later in calculus, you'll have to designate whether it's approaching 0 from the positive or negative side, above or below it. For here, we don't really care. And then on the right side of your function, again, it's approaching the asymptote from the other end of it, but it's still approaching 0. And behavior continuity. We already answered this. Was this continuous? Absolutely not. This is discontinuous at, you can just say x equals 0. That works for me. Later on, I'm going to ask you what kind of discontinuity. That day is not now. If you're curious, though, it's called an infinite discontinuity. And then I want to know when the function is increasing and when the function is decreasing. So this is the roller coaster question. This portion of the roller coaster track, is it increasing or decreasing? Decreasing, yeah. And then over here, this portion of the roller coaster track, is it increasing or decreasing? Decreasing. So it's never increasing. Would it be appropriate for me to say it's decreasing from negative infinity to positive infinity? No, because that would indicate it smoothly decreases the whole time when clearly there's a disruption. So you guys are going to tell me it's decreasing from negative infinity, and then at 0, something weird happens. And then it starts decreasing again on the other side of 0 to infinity. Nice. All right. There's a question on one of the versions of the test that looks just like that one, so make sure you guys are being real careful about how your intervals are written. Oh, I wonder what happens when we have a radical. I don't know. Let's look. Okay, on your calculator, this one I would like you to type, please. Could you get this typed into Y1? And it's a negative in front of a cube root. Make sure the quantity 2x plus 5 is being squared, and that is all under the square cube root, excuse me. Cube root. Y'all should see that when you get it. If you don't see that, make sure your window's appropriate. And then if you still don't see it, you have something typed wrong. So, what is going on there? That little cusp is what we call this. We're still going to treat it like it's a maximum of the function. So you should find that value. So could you use your maximum finder and tell me what ordered pair that is? And unless your window is something else, you're going to have some pixelation issues, and it's going to give you some weird answers. So just round to the most appropriate ordered pair here. I think it's negative 2.5 comma 0. Now, it probably won't tell you 0. It's probably going to do that scientific notation thing with the E, because this is a pretty rough pixel picture. Totally looks like that. Yep, nailed it. All right. So that's called a sketch. It's not an official... I didn't plot any points, clearly. I did a terrible job of graphing it. But there are arrows on each end of that curve. So my first question of what is your domain, it does go forever left and right. And you guys probably aren't really sure what to do about this thing. It's not a discontinuity necessarily for us. Technically, sharp turns are considered continuity issues in calculus. But let's not worry about that for today. It's not a smooth curve is what the issue is. So this domain does go from negative infinity to infinity. Any thoughts on range? Remembering range is a low to high interval for y's. I heard negative infinity to 0. Good. Now, some of you are still having trouble with what to do with the bracket parenthesis issue. Since we're claiming there is an ordered pair right here, we need to use a bracket. The only time you would not use a bracket would be if you have an infinity, if you have a whole, or you have an asymptote, which we don't have any of those things. X-intercept. This is where your book is going to get into a mathematical battle with another book. There are some books that say there is an x-intercept at negative 2.5. Your book says nay, because of the issue of it not crossing through the x-axis. Do you guys agree with that? Even on the calculator, I could kind of see it didn't really go through the x-axis. So your book is going to say that there is none. But if you told me there's totally an x-intercept at negative 2.5, right now I'm not going to count you wrong. That's okay. Y-intercept, however, that is not up for debate. There's most definitely a y-intercept. If you could please hit the trace button and then type in x equals 0, it will tell you whatever this number is. And it's not pretty, so I also didn't graph it well. What is it, negative 2.92 or something?
Yeah, negative 2.92.
Yeah, we'll go with that. I'm like a whole integer off, my bad. Alright, so y-intercept, no doubt about that, but the x-intercept, I'll take a few different answers. Are we okay on that? Like, technically there is not an x-intercept. Alright, so end behavior, well, that lovely template everyone loves. F of x equals, or approaches, excuse me, blank as x goes to the left. F of x function approaches something as x goes to the right. And if I look at both left and right end, I notice that both ends are moving down forever. So they are both approaching negative infinity. Alright, so we got end behavior. Okay, next question was, oh, I keep forgetting one. Are they asking about continuity? Yeah, I keep forgetting it. Is this continuous? Yeah, technically we will say it's continuous. Calculus has a different conversation to have, but for us, we'll say yes, it's continuous. The only thing you have to look for, holes, jumps, and then asymptotes, infinite discontinuities. All right, and then increasing and decreasing behavior. So think about a roller coaster. And when I look at this side, the roller coaster is going up, 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 and then it reaches a maximum and then goes down, down, down. So it's increasing from when to when? Negative infinity till when? Negative 2.5, good. And then it's decreasing from negative 2.5 to forever. Very good. Remember, increasing and decreasing intervals, those are domain intervals. They're asking when is your function showing a certain behavior. So it's x values. We get them all? Oh! Yes, we did. Okay. Good deal. Alright, on the back. Hope y'all ate your Wheaties this morning. You're going to need it. So if I had all the time in the world, which apparently I did when I first recorded this lesson, I would do every one of these questions that you see on the next few slides. Like, for instance, this one. I was just going to go through this with you, and you were going to watch me do this problem, and then you were going to cry a little on the inside when you realize how much work these problems can have. I have good news for you. Not every problem we're about to do has tons of work. When we get to the one that has tons of work, you'll know it. Because if you guys know anything about our notes, we don't really give you tons of workspace. So does it make you nervous that I gave you like 6 inches of workspace below the last couple questions? That can't be good. Alright, so we're not going to watch this one for the sake of time, but we are totally going to do one together. Can you find number 4? This one does not have tons of work, so don't worry. Okay, we're going to be solving radical equations, and there's no surefire way to get them right, but I can give you some advice what'll make your life better. You want to isolate the radicals. So if you can do that, you need to do that. If you have more than one radical in the problem, you should get sad, because that makes your life a little terrible. But the worst possible outcome is if you have 2 radicals on the same side of the equation sign. You don't want that to happen. So if you can avoid that, please do. All right. So good news. First one, you only have 1 radical. So let's isolate it. You're going to start by adding 6. And you have the cube root of x squared minus 1 equals 2. So algebraically speaking, I need to undo a cube root. So you're going to cube both sides of your equation. Raise it to the 3rd power. Well, this isn't too bad. You get cube root and cube will cancel each other out, and you still have x squared minus 1. And then 2 to the 3rd power is 8. So at least we've gotten rid of all the radicals. Now we have to consider I have a quadratic equation, so I have to use my favorite technique for solving a quadratic. This is a special quadratic that just has 1 variable in it, so I'm going to use the square root method. I'm going to add the 1 over, get x squared equals 9, and this time, just straight up solving, guys, you're going to get x equals 3, and what else could work? Negative 3, right? Because positive and negative here. Excuse me. So in true algebra fashion, Anytime a kid finds an answer of x, they box it in and then they move on. Well, that's going to be a problem today, guys, because when you solve a radical equation, you often create what are called extraneous solutions. So through your derivation of the solution, you get like polynomials that have multiple solutions, and when you go to check them back in the problem, they actually don't work. So there's ways to notice if they're not going to work, and sometimes there's no ways to really figure it out except for just plugging them in. So what I need you to do, and this is kind of a pain, you got to go back and check. You can check anywhere before you took care of the radical. So you can go all the way back to the beginning of the problem. You can go back to this line that I wrote in black before I cubed both sides. I'm going to go to this line right here to do my check. So it's the cube root of x squared minus 1. Does it equal 2? That's the question. All right. I don't know. Let's find out. When you plug in x equals 3 right there, you get 3 squared minus 1, which is 8. What's the cube root of 8? Check. And what happens when I plug in a negative 3 right here? What's negative 3 squared minus 1? Also 8. So check. So it's not the end of the world to check your answers, guys. It actually feels kind of good. I feel like I got my problem correct. Let's move on. So maybe you're a little nervous because my advice to you was like, oh my gosh, you don't want to have more than one radical. Well, this is the exception to that. If you have literally a radical equals another radical and nothing else in your problem, this is an exceptionally easy question. They're already on separate sides of the equation. All you need to do is just get rid of the radical by squaring both sides. This is really an Algebra 2 question. Sorry to bore you. Produced a linear equation, so you're just going to solve it like normal. Did you get n equals 12? Okay. And then true Algebra 2 fashion, kids get really excited about their answer. They box it in and then they walk away, but now we know that we have to check our answer. So go back to your original problem and you're going to have to plug in a 12 for me. And we're going to have to see if these equal each other and it works out. So 6 times 12 is 72 minus 3. Does that equal negative 15 plus 84? So, yes, because that's square root of 69, and that's square root of 69, and those totally equal each other. Check. All right, we're making good time. I'm going to warn you, though. 6 has quite a bit of work, and 7 has quite a bit more work than 6. So, use your space wisely. All right, good news. I have one radical in the question. But my other warning to you was like at all costs, if you can avoid it, please. You didn't have a chair, did you? Poor thing. You don't want to have anything with your radical if you can avoid that. So can you guys give me a quick algebra move that'll get my radical by itself? Yeah, just subtract that 21 over. So 4x minus 21 equals square root of 56 minus x. So now I have to get rid of the radical, so we're going to square both sides of our equation. You guys did an amazing job of understanding what I was hoping you would do on this question on the last couple tests. You guys remembered that this is like a full-out foiling question. So it's 4x minus 21 times another 4x minus 21. Here we go. 4x times 4x is 16x squared. And then you'd have, let's see, negative 84x, and then another negative 84x when you FOIL outside inside. So that's negative 168x. And then negative 21 times negative 21 would be positive 441. Okay. That's good. It's been a while. All right, equals 56 minus x. So then we look at our result, and it is a what type of equation? Quadratic. And a nasty one at that. Now, I'm going to give you guys a little advice, whether you want it or not. Those are some amazing coefficients we got here. You feel like factoring that? No. No, I do not. So even though none of you like it, what's the one method of solving that really isn't that terrible as long as you know the formula? Quadratic formula. Let's just do quadratic formula, okay? Now it does have to be in standard form, so you're going to have to add the x over. You're going to have to subtract the 56. And don't screw this part up, because every time I do this, I screw this part up, and then I have the wrong coefficients, and then I get the wrong formula, and it's a hot mess. So you have 16x squared minus, not that, negative 167x 385. Okay. All right, in order to use quadratic formula, you have to know what quadratic formula is. Someone rattle it off for me. That was superb. Thank you. Over 2a, you said? Yeah. Nice. All right, let's do this. Negative b. All right, so that'd be a positive 167. Plus and minus. Now, normally I have you guys square the b term, so that way I don't have to do that extra step on my calculator. But I don't know what 167 squared is. But I do know I'm not going to bother writing down negative 167 squared, because this term always comes out to positive because of the squaring. So I'm just going to write down 167 squared. Minus 4 times a times c. And then some of you are still doing weird things with this fraction bar, this vinculum. All the way under everything here, guys. 2 times a. Now, just because I just did this problem with first hour, I figured out that that comes out pretty nice. Can you guys go ahead and take the square root of your discriminant? Comes out pretty nice, actually. Beautiful. 57, yeah. So x is 167 plus or minus 57 all over 32. Okay, PreCalc, you're better than this. You can give me your two answers, right? What's 167 plus 57 quantity divided by 32? Ooh, 7. And then 167 minus 57, the quantity divided by 32, decimal's fine. It's 3 point something, isn't it? Okay. Oh, okay, so fraction, it's 55 over 16. Okay. So it's 3.44-ish. Okay. And don't you feel like we should be done? Like, that was a lot of work. But we're not! Because now I have to go back to the original problem and make sure that it doesn't provide any extraneous solutions. Now, it's possible that both solutions work. It's also possible that one of them is extraneous. It is also possible that both of them are extraneous. What would happen if you got two solutions and they're both extraneous? Then you have no solution. Very good. Let's see what happens, guys. X equals 7. If you plugged it into, and you can go to any line in your work before you squared. So, like for me, I like to go to this line right here before I squared. So if I plug in a 7, I get 4 times 7 minus 21 equals the square root of 56 minus 7. I don't know. Let's figure that out. This is 7. And this is square root of 49, which is also 7. So check, x equals 7 works. And then I'm going to go plug in roughly 3.44. And I'm not going to spend a lot of time on this part, because look right here, guys. If you plug in a 3.44 right here, you get like 13-ish minus 21. So you're going to get a negative number over here. Can you have a negative number equals a square root? So that one's extraneous. So you cross it off. You write ext next to it. You still got to show your teacher you got the extraneous solution. It's kind of annoying. But that's how you indicate that it doesn't actually work for the problem. And if you're not sure, just go back to the original problem and plug them in on both sides of the equation and see if it works out. All right, this one. Okay, we have 7 minutes, and it's going to be real close. You ready for this? What is the one thing I told you want to avoid at all costs? This. This exact thing right here. I said don't have two radicals on the same side of the equation. Like, it's terrible. It's terrible, guys. I'll be honest. This is going to be terrible regardless. So, can you think of anything I could do so I don't have two radicals on the same side? Add that one over. Sure, sounds good. All right. So, scrap this problem, and let's do this problem instead. Square root of 6x plus 12 equals the square root of 4x plus 9 plus 1. Great. All right, so let's square both sides. Left side, not bad. Right side, real stinking weird. All right, let's look. 6x plus 12, boring. When I square the square root, they just knock out. Can you talk about what's happening here, guys? You have the square root of 4x plus 9 plus 1 times another square root of 4x plus 9 plus 1. You are supposed to FOIL those terms together. All right, let's do this, guys. First times first. What happens when you times the square root of 4x plus 9 times another square root of 4x plus 9? You're squaring it, essentially, is what you're doing, right? Something times himself is the same thing as squaring. So the squaring factor and the square root will knock each other out, and you just got 4x plus 9. Okay, outside term. You have 1 square root of 4x plus 9. Inside term. You have another square root of 4x plus 9. So if you have 1 square root of 4x plus 9 plus another square root of 4x plus 9, you have 2 square roots of 4x plus 9. And then finally, something nice. 1 times 1. Nailed it. 1. Very good. All right. Let's see. What do you notice? You still have a radical. We got to start this process all over again. Get the radical isolated, okay? Oh, fantastic. All right, let's subtract the 4x over. Subtract the 4x over. And then I'm going to kind of cheat here because I know you don't have a lot of room. This is really a 10, so let's just do a cheater's thing here and say I'm subtracting 10 from both sides. So I have 2x plus 2 equals 2 times the square root of 4x plus 9. I'm still not quite isolated, guys. Do you see it would be a really cool move if you just divide everybody by a 2? Let's do that. So I have x plus 1 equals the square root of 4x plus 9. That's great. Now what do you have to do? Square again. Oh, this is just getting better and better. All right, guys, you were really good at this on the last couple tests. Let's do it again. X plus 1 quantity squared. That is a foiling question, right? So that's x squared plus 2x plus 1. And then squaring the square root factors will cancel. So you just have 4x plus 9. Guys, I have never been so happy to see a quadratic equation in my life. We are almost there. Let's solve this quadratic. I'll give you a hint. This one is really nice and factors really well. So let's get this in standard form so I can factor it. I'm going to subtract 4x over, so it's minus 2x. I'm going to subtract 9 over, so it's minus 8. Almost there, guys. X minus 4 times x plus 2 are your factors, which means your solutions are x equals 4 and x equals negative 2. And like in a perfect world, we'd be done. We're not done, because now what do we have to do? Check them. All right, spoiler alert. 4 totally works. Just pretend like we checked it. But let's look at what happens when you check negative 2. All the way back to the beginning of the problem. If you plug in a negative 2 in for all your x's, you get negative 12 plus 12 under the radical minus negative 8 plus 9, and it's supposed to equal a 1. Well, this is 0 minus this is 1. And what is 0 minus 1? Not 1. So that one didn't work. Great. All right. So the fact that this is extraneous is not bad news. It just, you got to show me that. Oh, these are fantastic. You guys are assigned bookwork 2.1. Have a fantastic weekend.